Late on a Sunday to hear me speak. It is definitely good to get back out and see people face to face, isn't it? Our first show was PPAI in Las Vegas, which was the first one since obviously before COVID, and it was still masked up for that. And this is really the first event that we've attended where we didn't even have to go through that. So it's good to see people's faces again. Well, before I get in, I thought I would do a little bit about who Marabou is, for those of you who might not know. I'll cover this very briefly. But what I'm going to be discussing is, I put my topic as kind of vague when I first put it in the program, because I wanted to see who else was speaking and about what were they speaking, so I didn't duplicate the topic. So we are going to be discussing the development of an industrial inkjet system and how that applies to glass and square decoration. But excuse me, tell me your name again.
Todd.
As Todd mentioned, we are a 165-year-old family-owned German business. We are still family-owned to this day. We have two facilities, one just to the northwest of Stuttgart and another one about 10 minutes away where we do all of our water-based and UV manufacturing. We have all kinds of inks and coatings, screen, digital, pad. We have water-based, UV curable, solvent, and we have more than 500 employees worldwide. We actually have about 20% of our employees are in R&D. I like to say we're an R&D company that sells ink rather than an ink company because we do a tremendous amount of R&D. We have 16 subsidiaries. The two most important as far as I'm concerned are Marabou North America, founded in 2011, and we opened Marabou Canada in 2019 just outside the Toronto airport. And what's interesting about Marabou is that we play in the industrial space exclusively. We manufacture inks for the tagless applications in the back of your Hanes and Fruit of the Loom t-shirts, automotive applications, medical applications, electronics, anything that has a real high difficulty of entry, meaning a product that has to pass unbelievable specifications. We're in the cell phone industry, on the backside of many of the cell phones' glass. But we like to say that on average, every human on the face of the earth touches our product 7 times a day. It's that prolific. And for a little company, by ink company standards, we're quite small. But it's out there everywhere. So, let me move. This is a graph that I created because I want to talk about the concept of why in the world are we even talking about digital anyway? What is it about digital? And most of you have a good understanding in your head, but I would encourage you, if you're a screen printer or a digital person, you need to develop this for yourself. What it is this is cost per unit, and this is number of units. This straight line right here represents digital. Whether you're printing 1 or 1 billion, your cost per unit is the same because it is just the cost of the ink. But when you're screen printing, you've got to burn a screen, and there's labor, and there's materials, and there's time. So what these curves represent are 1 color job, 2 color job, 3 color job, 4 color job. Now, I theoretically put some value on it. For example, I said 8 cents. That's about an average for a pretty good heavy coverage digital object. Screen inks, on the other hand, are significantly cheaper per square inch of actual coverage. So as you move and increase your volume, you get to amortize the cost of those screens into each one of those units. So the higher and higher you get, the closer and more asymptotically, this is math class, you will approach that. What I put in there was 2 cents for the ink. What you really have to do for yourself is, and I can send you the spreadsheet, you just plug the numbers in. What are you paying for the digital ink? How much coverage? And you will be able to say, okay, here's a job for 1,000 units. The 1,000 units is right here. If it's a single color job, you're probably better off going screen because your cost is down here. But if you're 2, 3, or 4 colors, suddenly digital is the way to go. That's just kind of a mathematical approach to it. Many of you probably have already developed that. But it's a conversation that has to happen when it comes to why in the world are we going digital? Some of the other important things, this is obvious, short run cost is a big driver of why to go digital. There's also, if you're looking at, if you're using inorganic inks and you want to get away from heavy metals and things like that, every one of the digital products is going to be organic, so you don't have to worry about heavy metals and those kinds of things. And also the number of colors. Because you've got CMYK, you can create, in theory, an infinite number of colors, or you don't have to go and worry about color mixing, color matching when it comes to PMS and those kinds of things. So, now that we've decided we're going digital, what do we do? What are the steps? You'd be surprised at the number of folks that come to us and say, I have a printer and I have this printhead in it, do you have an ink for it? And I go, well, shouldn't that be question number one? What I'm here to tell you is yes, it is. Number one question you have to answer is, what ink am I going to use for this project? Because ultimately, it has to meet the requirements. Does it have to be chemical resistant? Does it have to be low migration? Does it have to be safe for toys? Does it have to be like a gasoline resistant? There's all kinds of different things that ink has to do. Number one is make sure your ink can do it. Do a proof of concept. Do some kind of test. Just make sure your ink meets whatever requirements you've got. From there, you're going to choose a printhead. I'm going to talk about the design characteristics behind that process. And number three, then you build your printer, not the other way around. It becomes very, very expensive if you do this in the reverse direction. Very expensive. And I've seen it happen, and it's unfortunate. So this is very simple, right? 1, 2, 3. Ink, printhead, printer. I'll just talk about some of the intricacies of it. You saw what Paul's machine could do when Paul Baldwin was showing you some of the videos. Absolutely amazing engineering. But that is stuff that you put after step 1, step 2, step 3. So let's talk about just a little bit. So we're talking UV ink, digital UV ink here. And the blue represents the substrate. And this is the printed ink film. Consists of a UV binder, UV monomer, photo initiator, and some other goodies when you design an ink. You hit it with UV energy, and you create a chain reaction, a chemical chain reaction. The photo initiators create free radicals, and suddenly a process called polymerization occurs. The reaction is nearly instantaneous if you have sufficient energy input. There's the process of pinning is given just enough energy to keep it firm without going to that final cure. But when you hit it with enough energy, you have a nearly instantaneous reaction. And you have a full cure that's going to require up to 24 hours. So be aware that if you're going to test for durability or anything like that, give it at least 24 hours or put it in an oven. That will increase the speed of that reaction. So let's talk a little bit about UV ink and why it's different than most inks, like solvent inks, water-based inks, etc. It's because you have such a wide range of raw material that you can use. From the photo initiators to all the other elements, it's the selection of these items that allow you to tailor an ink to a very specific application, which is why requirements of the final product need to be mentioned up at the very beginning of the process. The length and the structure of these polymer chains and copolymer chains that are formed are what actually dictate how that ink performs under different situations. So here are two hexagons which represent a typical rigid UV ink versus a flexible UV ink. And these different axes are used to indicate how chemically resistant, how about our color density, flexibility, adhesion, odor. For those of you who've been around different digital inks, you'll notice that some of them smell really bad, really strong, and others, they don't smell at all. That's actually a function of the raw materials that go into the ink. Now, it would be fantastic if you could design an ink that met all of these requirements. You would be 6s all the way around. But the reality is that you just can't. Because an ink that's going to be flexible won't be hard at the same time, as you would guess. So you're going to give up a little bit in different areas. So in many cases, if you've got a really specific requirement, you can tailor an ink to do exactly what you want it to do. Now, if it doesn't have to be chemically resistant, great. You can forget about having to perform it on that particular axis. But what we have sought to do, in most cases, is we build an ink to be an all-around ink, meaning it performs as well as we possibly can on every one of these axes. Mamaki, for example, manufactures at least 4 different formulations of ink depending upon what the requirements are. And it can be very expensive to switch from ink to ink to ink to ink, or in multiple printers, depending upon what your application is. So ours was to design an all-around ink. That doesn't mean we don't do inks that are very specific. In fact, we did that with Cayman, exactly what we did with Cayman to produce the ink for that machine. Now a little bit about surface energy and tension. You saw a little bit about this from Michael from IDS earlier today. And this is just an underscore of that. I'm emphasizing the fact that this is your material surface energy, and this here is your ink surface tension. You want a minimum of 20 units between those two in order to get good droplet formation and good wetting on your material. Probably all of you have seen this at one point if you've done any kind of digital direct object printing where the ink just basically beads up, doesn't wet out at all. What does that look like? It's really a function of contact angle. It's kind of like when you drop a droplet of water on wax paper. It doesn't spread out at all. It stays a droplet. And you don't want your ink to do that, because if you do, you end up with those print quality issues that we just showed. This is an example of the kind of wetting you want to see, about a 45-degree contact angle. You can actually get worse than that. You end up in a complete wetting situation. What does that look like from a print characteristic? Too small, meaning if you've got the droplets are beating up, you end up with these striations. You want them to just overlap, droplet over droplet over droplet for good print quality. But what you don't want is the ink just kind of bleed into the other colors. You end up with inconsistent, low definition, etc. So this is a very important characteristic, is getting the ink to match the substrate. Get the substrate energy level up. This is just what Michael mentioned earlier. Now, another concept that you got to always be thinking about is what happens when you put white ink down first. No longer is the surface energy dependent upon the substrate. It's now a white ink film. If you're white ink film, and unfortunately UV inks, as you add energy during the pinning process of color after color after color, the surface energy changes, which creates all kinds of headaches. So here's an example of a white ink that was put down first and it was overpinned. And as a result of the overpinning, you end up with a real low surface energy. With that low surface energy, the subsequent layers that are printed on top of that result in really poor print quality. So ink design has to be taken into consideration. The printer's pinning lamps, the energy, all those things have to be taken into consideration if you want to ultimately get really, really good print quality, which is obviously the objective. Next is print head selection. Some of the things you need to be thinking about. Well, physical geometry of the head. What do you need the ink to do? Or what do you need the system to do? If you've got a really big head with lots of nozzles, that might be great if you're printing big objects. But if you've got to follow contours, if you've got to get a maximum throw distance and things like that, you really have to think about how big is this print head and why is that important? Viscosity range. I apologize for those of you who might not see it in the back, but UV inks, again, unlike other inks, they are subject to changing their viscosity as a function of temperature. So, you've got viscosity on this axis, you've got temperature on this axis. You'll note that the sweet spot for Marabou's DLEA is right here at 45 degrees C, which is roughly 12 centipoise, plus or minus 0.1. That's not by accident, that was by design, because many of your industrial printheads operate in that range. Konica Minolta, Kyocera, Ricoh Gen 4, Ricoh Gen 5, etc. So you have to make sure that the printhead you select is in fact going to give you the viscosity range you're looking for. Next is duty cycle. That's pretty simple. That's only to me, how long will this printhead last? How many droplet firings can I get out of it before that piezoelectric element fails? The reality is probably 90% plus of digital printhead failures are not a result of just wearing that out. It's usually a function of UV light being reflected or operator error, collisions, and things like that. We'll talk about that in printer design. Next is cost. Boy, these things are not cheap. Usually anywhere from the low $1,500 range to $3,000 to $4,000 depending upon your head selection. So obviously the cost of your overall system goes up as you add expensive printheads. Chemical compatibility is another big one. If it's done right, you will get from the inkjet head manufacturer a listing of all the materials. You'll actually get those materials and subject them to soaking in each of the raw materials that goes with your ink. You check the viscosity for changes over time. You check for any swelling of the components and anything that would indicate any type of chemical compatibility issues. And most of your printhead manufacturers will give you a listing of the things that are both compatible and incompatible with their particular printhead. Next is frequency, and that's just as simply as how fast can this piezoelectric element fire. Years ago, the numbers were down in the low teens. Now we're talking about printheads that are firing 60,000 hertz, 60 kilohertz and higher. And that's really a function of how quickly can you make this overall system perform. Next is drop size and variability. When Epson, which was one of the very first print head piezoelectrics on the market, they came out designing printers for printing photorealistic output. So you could look at a photo and go, that's beautiful. So they're in the neighborhood of 3 and 4 picoliters. Way overkill for this market. That's why most of the market has gotten away from the Epsons and gone in the direction of industrial, which are your Kyoseras, the ones that I just mentioned. So too small of a droplet is also going to prevent you from throw distance. If you have hardly any mass, the ability to throw a droplet at distance is going to become significantly reduced. Kind of like the difference between if I have a baseball in my hand and I have a puffball in my hand, I can throw a baseball at the other end of the room, but a puffball is just going to meet the natural resistance of the air and it's not going to go very far. So that's also an important consideration. In a minute, we're going to talk about how you can overcome a small droplet by making it a bigger droplet out of the same printhead. Then there's this concept of viscoelasticity. What in the world is that? So you can take two identical liquids and you can measure their physical properties. Everything from surface tension to rheology to viscosity, everything. And they can be absolutely identical. But those are all static measurements. It's being measured on a static liquid. Once you put that liquid in motion, everything changes. That's called viscoelasticity. So just because you've got an ink one and you design your ink to match the physical requirements, there is no guarantee it's also going to perform under the stresses that are ongoing inside printing. And if you got everything right, this is what you should see. This is a time lapse of a droplet being formed. You can see it's being ejected, and it comes out with a tail or a ligament at the end. And as the droplet moves forward, this ligament should close in and become a single droplet by the time it strikes your substrate. That's a really good, nice round droplet. Fantastic, you did your job. If you see things like satellites and improper print quality and stuff that doesn't look bad, usually, or doesn't look good, it's usually the function of this ligament breaking and the tail spinning out of control and striking outside of where the original droplet struck. You get really bad results. Or if you get an oblong-shaped droplet that isn't properly formed, that's what you get. So how do you make sure that you're getting the best droplet? Waveform. Waveform is a very important consideration when it comes to these printheads. All this represents is voltage over time. You get a single pulse, you get a small drop. You go double pulse, you get a bigger drop, because, I'll show you in a minute, you get 3 pulses, you get an even bigger drop. What you end up doing is you're injecting a small droplet, you're injecting another one right behind it, but you'll notice the amplitude is increased. Why? That's because it has to move faster, because it's got to catch up. It's got to catch up to that first droplet and become 1 droplet before it hits the substrate. You can do the same thing even with a 3rd droplet. So, for example, Ricoh Gen 5 printhead has a native droplet size of 7 picoliters, which is kind of small. What we like to do is hit it with double pulse so that we can get ourselves to a nice 14 picoliter, which is really nice droplet size to give you good definition, get good opacity at the same time. So what does that look like? Here we have a drop watcher system, which is a high-speed camera that is looking at the droplets as they come out of the printhead. And in this case, it's technically 3 pulse, but we'll call it single pulse for the purposes of our definition and our discussion. Here you've got a single droplet being ejected, and you've got the tail breaking off, but it gets closer and closer and closer, and hopefully it forms 1 droplet by the time it gets to the substrate. In this case, it looks ugly, but you end up with single pulse, double pulse. And the 2 droplets, as you go forward in time, will eventually merge and form a single droplet. Now, this is an optimized. What would be optimal is if this never broke loose, and it just didn't have to worry about the tiny little piece catching up to it. So this waveform development, there's a couple of companies that do it here in the United States. In fact, we don't do it. We have our own system over in Germany, but we don't have one here in the US. I'm actually using a US firm to create some custom waveform developments for me right now for a project we have ongoing. But this is a very important aspect, making sure that you've got your output quality. It's going to be a function of that droplet. And if you're not getting good droplets, you're not going to have success from the very beginning. So then the last piece is hardware design. That's when you know you've got it in, you know you've got a head, you know you've got everything that you need except for, I need something to build me a commercialized printer around this thing. You gotta ask yourself, do you want multi-pass or single pass? Single pass means it's only passing underneath that one print head one time. Multiple pass is scanning or rotational. Then you've got to ask yourself, do you want helical or sequential, the way that you stitch each line of data from one to the next? Then there's the number of heads. Usually, the speed of a system is limited to the number of nozzles available to fire. And one way of increasing the speed of something is just simply add another set of print heads, or another set of print heads, but guess what happens to your cost? It goes up and up and up and up. Lamp, power, and orientation. You've got to make sure you've got enough purity energy inside that printer to cure your ink. You also have to make sure that you don't have too much UV energy bouncing around inside there, reflecting up into the bottom of your print head. Typically, you'll find, you'll notice from what Paul discussed with their digital machine earlier, is they actually shutter the head before they turn on the light, so they protect their heads from UV energy. Unfortunately, there are some designs of printers out there where the UV lamp is directly beneath the print head, which is why many times you'll find customers or operators are having to stuff a clear jar, for example, or a clear plate glass with something that's going to block that UV energy from frying those heads. Like I said, that is probably the number one killer of print heads is improper operation. So if you can come up with, in your hardware design, a means by which you can protect those heads no matter what, that's going to be a much more cost-effective system in the long run. And then, physically, how you move this stuff around, into the printer, out of the printer. How do you move the print heads? Do you keep the print head stationary, or you move the substrate, or vice versa? Unbelievable stuff. I've never seen those videos, Paul. It's fantastic. But the German engineering just blows me away. And then there's the concept of meniscus pressure and temperature control. As we mentioned, ink has to be heated up. So you've got sub-tanks in the printer that raise the temperature of the ink so that when it's drawn from the sub-tank down into the print head's also heated, you get nice, consistent temperature control. So your droplets remain the same. The other is meniscus pressure. It's kind of like a straw. If I took a straw, put it in a drink, and pull it up with my thumb over the top, nothing's going to come out the bottom until I release that and allow air to go into the top. It's kind of the same way with UV ink in a digital printer. You've got to have some type of a level of vacuum that keeps the ink from just simply draining out of the heads. It would happen if you turned off the vacuum. So every one of these printers is going to have a control over meniscus pressure. One of the mid-level printers I'm going to show you here in a minute, designed by the company Elsync, those were the engineers that were at our booth yesterday. They have actually developed a patented process by which they are looking ahead at the amount of data that's coming to this printhead, which means the amount of ink volume that's going to be flowing through that channel. And they will begin to relax the meniscus pressure, meaning that they're going to allow more flow because they're anticipating it coming. It keeps you from starving your printheads under high demand situations. Pretty fancy engineering, to say the least. And then I mentioned it already, which is that's head protection. You don't want to pay an engineer to operate one of your printers. No. So it's one thing to make a printer that an engineer can make print. It's completely another just to hand this off to an hourly operator and say, go produce 2,000 units for me today. The problem is, not only is UV energy an issue, but what if that person loads the wrong recipe or loads the wrong piece and the printheads think it's going to print and they end up smashing directly into the material? Happens a lot. So you need to make sure that the hardware prevents any and all errors from occurring so that it detects an out-of-round condition, it detects a size that's larger than it was supposed to, it should shut everything down and throw an error code before it actually harms the printer. And then drive electronics. Those are just the wires and everything that makes the heads flow. And then the HMI, which is the human machine interface. That's the screen you look at, the RIP that you deal with, how to control the equipment. So, the good news is you don't have to do that. You don't have to figure all that out. In some cases, we get clients that often do that. They come to us and they say, here's what I want to do. Can you help me do it? The answer is absolutely. Let's go step one. Then I'll take you over to the integrator. And the integrator will then just take proper printhead and then build you a commercialized machine. We've got plenty of projects that are ongoing doing exactly that. But in the case of glass and ceramic decorators, bottle decorators, can decorators, etc., there are already solutions that are out there on the market today. And we tend to classify them in different levels. Level 1 is your entry level. And usually cost and speed are what characterizes each of these machines. Level 1 would be a machine that's, I don't know, somewhere in the neighborhood of $150 to upwards of $250,000 to $300,000. But the throughput speed, 2 to 5 maximum for most of the machines that you see here. This is the Quad Rev by Innovative Digital Solutions. This is the Bottle Jet by Engineering Print Solutions of Vermont, and the Helix by Ink Cups. Good machines, all of them, but they're not that fast. They're great for people who are just testing, getting into the digital market. I know some companies have upwards of 30 of these machines just because they need high throughput. They like the redundancy. It depends where you are with it. The next, which I'm calling level 2, is a company that we became familiar with earlier this year based out of Huntsville, Alabama, called Helsinki. And what you get out of this machine is similar printing characteristics as the level 1, but in this case, they've got 4 tunnels operating simultaneously. So you're now going from maybe 5 per minute, now up to 19 or 20 per minute. So significantly faster. And then, if you want to talk about the big boys, the ones that are doing massive amounts of throughput, like the Cayman machine, we have a customer, PSL, that has a sister company, Druckers, that worked directly with Cayman over in Germany. Paul and I talk about every other month to say, okay, what have you heard? What have you heard? We're comparing notes all the time to make sure that we're staying abreast of what our 2 parent companies are doing over in Germany. And then another that I haven't heard much from lately, but a company by the name of Till has put together a printer that's basically an array head, a circular tube of array head, super expensive. But they ended up taking a cylindrical object and shooting it through this array in a rotational method that actually is a single pass decorating technology that is being targeted at your Coca-Colas and your Anheuser-Busch's and all those others. Haven't seen it commercialized yet, heard a lot about it. You may hear something in the future, I don't know. So, good news is we have solutions that are already there. What I'd like to close with is a final, almost funny story, but could have been not funny. Has anybody heard of Crazy Mason? It's a milkshake bar. It's primarily in the Southeast. There are about 7 different locations. There's one in Myrtle Beach, there's one in Asheville, there's one in a new one just over in Mount Pleasant where I live. But Crazy Mason sells these massive desserts, which is really nothing more than diabetes in a jar. Unbelievable amount of calories, but they're all glass. And what happened was a company by the name of Herald Graphics is undergoing a generational change. The next generation of gentlemen are now stepping into the leadership role of this company. And Herald Graphics is a company that all they do up until now was newspaper and brochure printing via offset. And it's old machine. Well, the younger generation comes in and says, you know what? We're going to change our business model a little bit. And we spend so much money on marketing day in and day out. Maybe it was just enough because one of the younger gentlemen called Maribou, just a cold call, and spoke to Sid. Sid happened to take the call. And he said, hey, I need to print on this particular glass, and I need durability, etc. And I said, just put on my voicemail. He said, no. You need to take this call. I said, okay. So I started talking to the guy, and he's telling me about the volumes that he's going to have to produce. We're talking hundreds of thousands. And I said, how many different images? And at the time, it was only five branches. And I said, well, you really want to go screen. You really want to go screen. Let's find you a screen print equipment manufacturer that we can give you our ink that'll run on it well. He refused, wanted nothing but digital. I said, okay, no problem. What we'll do for you is, let me introduce you to Paul King, because they have a machine that's not only digital, they have one that's hybrid, screen and digital. It'll be perfect for you. He said, well, that sounds great, but, I said, what do you mean but? He said, well, I've kind of already taken the order, and it's due in a month, and I don't know how to print it. I said, you gotta be kidding me. So here's a guy who knows nothing about direct object printing, taking a job for hundreds of thousands of units. And it just so happened that we were meeting with Elsie and just starting our relationship with this Huntsville, Alabama company. And we became aware of the Paracube, the four spindle machine. And I mentioned it to Harold Graphics, and they said, I want to go see it. They got on an airplane, flew straight to Huntsville. They looked at it, they said, not only do we want to buy this, we want to buy your Pyrocell machine, and I need to have it delivered in 3 weeks. And they looked at him like he had 4 eyes. But ultimately, they said, okay, we're going to make this work. So that's what they did. They boxed it up. They took everything to their facility in Dillon, South Carolina, and they began the installation. Well, I was there, and my technician, Jason, was there, and we were assisting as well as we could, and I noticed it was getting late in the day on a Friday. And it's 9 o'clock at night, and more people were showing up. I'm thinking, what's this? What is up with this? I come to find out they were there to begin production on the machine as soon as the engineers said, okay, it's ready to print. I said, are you kidding me? They had 2 tunnels of the 4 operational. By about 10 p.m., they said, that's good enough, get out of the way. I need to produce 5,000 by tomorrow. So we stepped back, and these brothers and cousins jumped in on this equipment and ran 5,000 samples by the following morning, put them on a pallet, and drove them to the customer. Success story where we snatched failure from the jaws of defeat. But I have a little bit of a video here to show you. It's going to show, this is just my mobile phone. This is not a professional video by any means, but it's really cool. The first piece of equipment you'll see is the RLS equipment that takes Sean Lanigan's Pyrocell and applies that to the glass. The next thing you're going to see is humans taking those glasses and wiping them with the Marabou P5 primer. A very not great step in the process because it slows things down. Then it's going to go into the printer, it's going to get printed, and this person's going to take off the outfit. It's got automatic grippers that put the objects in and out. If you saw the video yesterday, it'd be a little bit better explanation. They have since worked with RLS to implement a spray process for the P5. So they'll never touch the P5, it goes right through a spray booth. That gets installed later this month. But here's just a quick video. In theory, the machine just take off. Oh, there it is. So there's the accumulation table. The first set of flame is burning off impurities. Second set of flame is depositing the Pyrocell to the outbound table. Here we have the manual wiping of P5, which is required definitely for durability through hundreds of dishwasher cycles. And now here you have the printer. Again, just 2 of the tunnels were operational. In it goes. Helical print process, UV light. UV light, however, is at an angle, not beneath, so you don't have to worry about stuffing something inside. Out it comes. Out to the discharge, quick QC inspection, into the box and on the pallet. So, went through a lot very quickly. How am I doing on time?
A little over.
A little over?
A little over. But I started you late. So.
You did, you started me late. Questions? If you come up with questions later, my contact information is listed in the brochures and stuff. Feel free. Love talking to customers, love helping them with their printing problems. Yes, Paul?
Is that around the machine work?
Yes, it is. Yes, it is. It will not, the LCD machine you were asking about will only do cylindrical objects and conical objects. Will not do oblong, will not do anything beyond that.
Go ahead and pull the next one.
Yes?
Is Helsinki currently part of INX or are
They were never part of INX. They do purchase the printhead electronics through INX because INX owns that technology.
How long did it take to get the other 2 tunnels up? I never heard that.
How about next day? How about next day? As soon as they said, okay, we've met the delivery requirement, the engineer jumped back in and brought the other 2 tunnels.
That's awesome.
Yeah. So they have since produced more than 300,000 of these objects through this printer in Dillon, South Carolina. And this printer is one that's, it's the mid-range. It won't do the volumes that the Cayman can do, but it does way better than those single units that take, 2 minutes or 1 minute to produce a print job. Very popular machine so far.